Today we will learn how to get information on f, on the shape of f, knowing information on the derivatives. So the first important result is the test of monotony. Test of monotony. So what does it say? It says that if you have f prime x, the derivative positive, okay, positive on an interval, then let's say an interval, let's call it I, then f is increasing, is strictly increasing on this interval. If you have now the derivative negative on an interval I, then f is strictly decreasing on I. Okay, so this is the first result. Okay, so yes, the proof now is important. We will give it because it is based on the mean value theorem. Here we will see it how it involved. So let x1. So let two x values x1 less than x2. x1 and x2 are in the interval I. And yes, so we have everything, or the assumptions on continuity and derivative and differentiability. So we can apply the mean value theorem on the interval x1, x2. So mean value theorem on, so apply mean value theorem on the interval x1, x2. So we will have fx2 minus fx1, okay, equal to f prime at an intermediate point and times x2 minus x1. Now let's discuss what is happening. If you have if we assume that the derivative is positive on the whole interval and c is inside this interval, then so necessarily we have f prime c positive, and we have also x2 minus x1 positive. Then necessarily fx2 minus fx1 is positive, that is, which is equivalent to say that fx2 is greater than fx1. You see, we started from x1 less than x2 and we showed that fx1 is less than fx2. So our function f is increasing, strictly increasing. Okay, so you see the key for point for proving this result is the mean value theorem. Okay, so let's do the following example. Let's explore the following example. So here is my function fx, 3x4 minus 4x3 minus 12x2 plus 5. Okay, so the derivative, yes, we want to know where the sign, study the sign f prime, so that we get the monotony. Okay, so let's compute the derivative. So it's 12x3 minus 12x2 minus 24x. We have 12x as factor, so we will have x2 minus x and minus 2, which we can factor and get the following factorization: x plus 1. Okay, so it is enough to study the sign of f prime so that we can deduce the monotony. So a way to study a sign, if you remember, you can use a table, okay, for factors. Okay, so let's continue. So we have three values here that will be that they are involved here, -1, 0, and 2. So for x, the first factor is 12x. 12x is positive if x is positive. So positive here, equals 0 here, negative elsewhere. X minus x plus 1, positive here, okay, positive, equals 0 here, negative. And x minus 2 will be positive here, negative here, and equals 0 here. Okay, so we can conclude now the sign of f prime of x. So product negative gives us negative, positive, negative, and positive, equals 0 at this point. So we have the critical points, 3 critical points. So -1, 0, and 2. F prime is, so f is increasing, okay, for x, if x belongs to the interval -1, 0, union 2 plus infinity. You see it here? You see here, we have here this interval, and here we have our function that is positive, okay? And you see that your function here, f prime, is negative, so your function consequently will be decreasing on this interval and on this interval. So let's add here minus infinity and here plus infinity. So f is decreasing if your x is minus infinity minus 1 union 2 plus infinity. Okay, great. Now, yes, what else? So always with the first derivative, the information given by the first derivative, we can have another, yes, test. We call it test first derivative. Okay, so let's write it here. Test of the first derivative test. Okay, let's call it first derivative test. So what does it say? It says the following. So I will express it just graphically. I think it's much better. So let's suppose that you have a curve here, situation where here is your critical point x0, and you have your function. So the derivative is positive. That means my function will be then, we said we have critical points, so we have horizontal tangent, and we have it is increasing and then decreasing. So we have tangents here that are f prime positive, and but here the f prime are negative. So you see what happens here. If you have then, so a critical point, okay, so you have f prime at x0 equals 0, f prime x0, f prime x negative to the left, okay. So I will express it like that. I prefer to understand what is happening. Okay, so f prime x negative to the left, to the right, so positive. Okay, positive to, for this situation we have positive to the left, f prime x negative to the right of x0, then we can say that x0 is a local maximum. So you see how there is this time we find the characterization, okay, for the critical, the candidate point. Okay, so you have a test here. If you can check the sign to the right, to the left of your critical points like that, you can say that it's a local maximum. Similarly, you have a situation where f prime x0 equals 0, f prime x negative to the left of x0, f prime of x positive to the right of x0, then x0 is a local minimum. Okay, is a local minimum point. Okay, so this is the information given for us by the first derivative. So for our situation here, as an example, for here, we see that we have at -1, you see here, at -1, the derivative is 0, but it's negative here and positive here. So decrease, increase, so we will have a local minimum. So we can say here that -1, x0 equal -1 is a local minimum. Okay, x0 equal 0 is a local max. Okay, you apply, just you read from the signs the information, and x0 equal 2, so decrease and increase, so is a local mean. You see how it is useful. Okay, the second, now suppose that I'm trying with these informations to try to graph my function. Okay, so let's try to do it. So I will draw the graph. So we have three values, x, y, and let's use, okay, let's say here is -1, 0. The value of the function at 0 will be 5 units. Let's say 5 is here. Okay, here is a point, so we have horizontal tangent. At -1, f -1, so I give you the values. F at -1 is equal to 0. F at 0 is 5. And f at 2 is -27. Okay, so I have an horizontal tangent, and the other one, let's say -27. Okay, this is 5, 4, 2 here, and they have another point here, you see. So I know that I have at -1 a local mean, so I will have a shape like that locally. At 0, I will have local maximum, I will have something like that. And here I will have a behavior also minimum point. Okay. Now, if I try to connect this, if I want to connect, if I try to connect these points, then it will not easy for me, because there are many, there are many possibilities. Do my curve behave like that? How can my curve do something like that? Okay, then later also here how it does. So here there is no extreme point like that, so it cannot happen. But if it is still increasing, how does it increase? Does it increase growing like that? So I need to know the global shape, the exact, what is the shape of my function. This information we can get it studying the second derivative. Okay, and it's a property that we call convexity concavity of the function. Okay, so we will say that let's give the definition of the concavity. So definition, okay, f is concave if f is concave is concave, okay, f is concave if f prime is decreasing. Okay, f is convex if f prime is increasing. Okay, now since we know the characterization of monotony, so if our function is regular, is very regular, yes, is regular, then we can say that if we have f second of x positive on an interval I, that means if it's positive, that means f prime is increasing, then f is convex, then f is convex. convex on I. F second negative on I, then F is concave. So what happens with this convexity? Okay. So when we say that F prime keep increasing, that means the slope keep increasing. Okay, decreasing, a slope that decrease will give me, look, if my F prime, let's just try to guess what is happening, the shape, what are the consequences of geometry. Okay, yes. So if we say that F prime, for example, is decreasing. So let's try. So I have, I start from tangent like that, slope like that, then my slope is decreasing, so I will start more like that. I start like that, then it will be like that, then it decrease, reach zero, continue decrease, okay, decrease, negative. It started positive, negative, okay. F prime here negative, F prime here is 0, and F prime here positive. So no, is positive here, sorry, positive it is, you see the inclination, but here it's negative. Okay, so you see the shape, this is a concave, the case of concave, okay, function, and a convex, let's imagine what is happening here. F prime decreasing, so let's don't mix between the sign and the monotony. Okay, F prime, let's write it sentence, decreasing, increasing. Okay, so this is the shape, and when F prime is increasing, then we will have the slope, so starts like that, small, negative, okay, negative, but start to increase, bigger, becomes 0, increase, positive, and increase, etc. Okay, so we will have like that, F prime from negative to F prime equals 0, then to F prime positive. So this is a convex shape of the curve. Okay, so usually convex, this is a smile, okay, smile, and this is, I think, a sad face. This one is sad face. Okay, so this is the idea of yeah. So if you come back, so here it's more complicated, so we'll not study this function. So this main idea, studying the sign of the second derivative, gives you more. Okay, the second derivative, so gives us, the first derivative gave us the monotony, okay, and a test for critical points. There is another test that second derivative gives us, is the second test derivative about the inflection point. So first derivative, so all that information are given by, okay, by the first derivative. Okay, and now we saw here something about the second derivative. Okay, so second derivative gave us the following. And the first derivative gave us also the following. Okay, great. Okay, so we said there is one more theorem that that we need to know. Second test derivative. Second derivative test. Okay. Okay. Second derivative test. So here is what it says. It says the following. If you have, so we have uh, this is also characterization about the critical points. Okay, so you have f prime of x0 equals 0, and you have and f second at x0 positive, then x0 is a local minimum, local mean. Okay, if you have critical points and f second at x0 negative, then x0 is a local maximum, is a local max. Okay, okay, so the last situation, f prime x0 equals 0 and f second x0 equals 0, no conclusion, no rule about this. Okay, there is no rule, anything can happen. I spoke about the inflection point. I need to give this definition. So about the inflection point definition, x0 is f second of x0 equals 0, and f second changes sign at x0, then round, I mean, it's not well expressed. Okay, round x0, okay, around x0, then x0 is an inflection point. Inflection point. It's the point where the function is changing its concavity. Okay. Okay. Yes, that's all. That's all. So second derivative test, second derivatives, we have second concavity characterization of concavity convexity. Second derivative test, you can use it for, it's much better than the sign, because here it's much easier. We can compute just the value of second at x0 and see the value, is it positive or negative, and we can conclude about local minimality or maximality. Okay, it's much easier. So mainly this is what I wanted to know, to tell you. So this is what we learned today. So let's summarize this, what we learned. So you see, we had so first derivative properties, we monotony depending on the sign of f prime, and characterization for the critical points, or their local minimum, local maximum, depending on the sign, both sides of x0 of the first derivative. Then we defined what is concavity, convexity, and so it was related to the monotony of the slopes. And then that means we could have the sign, studying sign of second derivative when our function is differentiable. And now then where it is convex and where it is concave. Again, we have another test, second derivative test for the critical points. Okay, for the critical points through using the second derivative. See, and the point where the function is changing the concavity is called the inflection point. Okay, so this is what we learned today.